Hello. I'd like to take a few moments to go through some of the topics that you're going to want to review for the final exam. If you're taking this course in the fall or the spring semester, you'll likely have the final exam in two parts. There'll be a day one and a day two. There won't be a specific number of topics on day one or certain topics on day two. They're going to be mixed together on the exam. If you're taking this course in the summer, then you're going to have just one exam, and that one exam I'm going to allow an extended period of time. So it will be a little over 2 hours for you to take that exam for the summer. In the typical fall or spring semesters, you'll have two course periods. So again, a little over 2 hours, but in two 1 hour sections. So things that you're going to want to make sure you know. You'll want to make sure you know limits. Make sure that you can both graphically and numerically evaluate a limit. You also want to make sure that you can analytically evaluate limits. And more importantly, probably make sure you know your analytic evaluation. That's, I guess, a major push, a little stronger than the other two. Not that you shouldn't know those things. But do know the two major techniques, the dividing out and the rationalizing methods that we used. As we evaluated limits, specifically limits where we would find a 0 over 0 indeterminate case. You'll also want to make sure that you know and can use the epsilon delta definition of a limit. So in other words, make sure that you can find delta given a generic epsilon or even a specific epsilon. Make sure that you can evaluate infinite limits. So as you are taking a look at limits, as they approach a one-sided limit, for example, of a vertical asymptote, make sure you can determine analytically, graphically, and numerically whether that's a positive or a negative infinity. So make sure that you can use those. Also, limits at infinity, so the limit as x approaches infinity. We had a technique where with rational functions we divided both the numerator and the denominator by the highest power of the variable in the denominator. So that was one of our techniques to determine what that particular rational function approached. And remember, if the degree of the denominator was higher than the degree of the numerator, that would approach 0. If they had the same degree, then typically it was some horizontal asymptote. If the degree of the numerator was one more than the denominator, then we would have an oblique or slant asymptote, and that limit would be infinity. Would be equal to infinity. Make sure you also know the limit definition of a derivative. So that's the limit as delta x goes to 0 of f of x plus delta x minus f of x all divided by delta x. Make sure that you can evaluate that. There's very likely to be a question where you have to find the derivative using the limit definition on the final exam. So make sure you can do that. And in general, you want to know all of your differentiation rules, whether it's a constant, power, product, quotient, chain rule. Make sure that you can apply those. And there could easily be questions where you have to find different derivatives or equations of tangent lines and slope. I don't have all of these things listed here on this review topic sheet, but in general, these are going to be more encompassing and general types of things. Make sure you're familiar with your position, velocity, and acceleration functions for falling objects. Our acceleration functions were typically constants, either 32 feet per second squared, negative 32 feet per second squared, or negative 9.81 meters per second squared. We encountered this both in differentiation, but also we encountered these in integration as we were finding some of the antiderivatives. And know that the derivative of position is velocity, the derivative of velocity is acceleration. So that means the second derivative of position is acceleration. Make sure you can also use implicit differentiation to find derivatives and second derivatives. And we also had the technique of logarithmic differentiation. You want to make sure you know your log rules, those 3 log rules, so that you can expand or condense logarithmic functions. And we use those in other instances as well throughout the course, so make sure you know those. Related rates, again there, you're going to be looking for maybe a particular rate at a given instant or time. You want to make sure you get an equation that relates all the variables that you either have rates for or that you want to find. And so that's a good application problem. The extreme value theorem, it's where we're looking for maximums and minimums on a closed interval. We have to check all of our critical numbers, but also have to check our endpoints. So make sure you do that for the extreme value theorem. I'm going to scroll here a little bit more. We had Rolle's theorem and the mean value theorem. That's for derivatives. You want to make sure you know your hypotheses for both. The Rolle's theorem had the 3 points. One, continuity on the closed, differentiability on the open, and your endpoints had the same values. That would give you a point on that interval for which the derivative is equal to 0. The mean value theorem was a little bit different in that all you needed was continuity on the closed interval, differentiability on the open interval, and then the slope of the tangent at some point would be equal to the slope of the secant, the average rate of change on that interval. And we saw many different applications and things of that nature. We also looked at differentials, and we had error propagation there. We looked at Newton's method, which was an application of our tangent line as we were trying to find zeros of a function. Make sure that you can find the intervals of increasing and decreasing for an original function. We did that as we were starting to examine functions. So taking a look at the sign charts of the first derivative. Number 16 here, intervals of concavity. So there you're looking at sign charts for the second derivative and determining those inflection points where we had changes on concavity. Relative extrema, where we are going to look at those critical numbers and then either use the first or second derivative tests to determine whether they were maximums or minimums. You may be asked to find some relative extrema and then use the first derivative test, and so you want to show your work so that it's clear to your instructor as he grades your test that you used one of those particular tests and that you can determine whether that's a maximum or a minimum without looking at the graph. But of course you can look at the graph and you can use your graphing calculator to back up and to supplement your answer in terms of checking your work, but you want to make sure that you can do the handwork here, the paper and pencil work, and make sure you can show that work on the test. Also optimization, basically story problems where we're finding those extrema. We had a whole section on those. Then we moved into the area underneath the curve, and that was our last chapter where we were looking at lower and upper sums, and we also had a limit definition of a definite integral. Here's where we had our delta x, which was uniform, and that was b minus a divided by n, and we typically used the right endpoint as our c sub I, so c sub I was equal to a plus I delta x, and then you could go and set up that particular summation and use your summation formulas to evaluate those and then evaluate the limit. So you want to make sure that you can use those and figure out what those are. You also want to make sure that you can approximate area underneath the curve using either a lower or upper sum. And if I do that on the test, it'll likely be a small number of rectangles just to make the work go quickly. So we're looking at 4 to 6 rectangles. Make sure you can find the area, and that's what we're setting up in terms of our definite integrals. So the integral from a to b of f of x dx, and you're using your fundamental theorem of calculus in order to evaluate that. Make sure you can find the average value of a function. That's using the mean value theorem for integrals. F of c is equal to 1 divided by b minus a of the integral from a to b of f of x dx, that average value on a particular interval. We had some methods to find our integration. So we had u substitution, and remember in there we had our backdoor method for finding an integral. We also had natural logarithmic integration. The integral of 1 divided by x dx is equal to the natural log of the absolute value of x plus c. And make sure you do remember your plus c in every single case. We integrated trigonometric integrals. and so we had all 6 of them now by using the natural log. So of course the integral of tangent of x was equal to a negative natural log of the cosine, absolute value of the cosine of x. The integral of secant was the natural log of the secant of x plus the tangent of x in absolute values. Make sure you can also integrate with your inverse trig functions. You had those 3. You had arctangent, arcsecant, and arcsine. And one of the methods that we used in that particular section was the method of completing the square, so make sure you're familiar with that. And in general, just know all of your basic integration rules. You can check those out in Chapter 5. They've got them all listed there, including those inverse trig functions. We did skip over a few sections in Chapter 5, but those sections will pick up and cover those when we continue in Calc 2. But if you have any questions over this material, please don't hesitate to ask me. If you're in the summer session and you're completely online, you can set up an appointment with me and we can meet online using WebEx, and we can have a virtual classroom where we can talk about some of these problems, and we can go through examples. If you're on campus in the ICN class or just in a regular face-to-face class, we can certainly go over examples on our review day. But I wanted to just put these out here, these different topics, and encourage you to go back and to look at the videos that I put in this particular class, look at all of your notes that you've taken, and just practice, practice, practice. As I've said from the very beginning of this class, you need to practice. Math is definitely not a spectator sport. In order to get good at mathematics, you have to practice mathematics, and you have to stay up with it. So I would encourage you to be practicing and to ask questions, and let's have a good final exam. Thank you.